Hi, everybody. I'm Keith. I'm a software engineer at Stripe. And this is Ian. Oh, I'm really sorry, guys. Hold on. Ian!
Oh, sorry. I must have fallen asleep.
What? The talk is starting. What were you doing?
I was waiting for Basil to build our new payment service.
Oh, God. Well, you know, I was just looking at some charts, and you're not alone. I just checked. And if you add up all the time that Stripe engineers wait for Basil every day, you get 150 hours per day. We're paying 10 engineers every day just to sit and wait for Basil.
But so why does it take so long?
You know, that's a really good question. I noticed something weird, though. All of our microservices are not really very micro. They have a lot of dependencies. What were you building?
Just our new payment service.
Oh, God, that one is the worst one. Look at that. It has 1,400 Java library dependencies. Can you believe that?
Do we really need all those dependencies?
That's a really good question. So we looked around and we noticed that our microservices, even from a bare scaffolded new service, have so many dependencies. And we just felt like this didn't pass the sniff test. We couldn't believe this was true. We felt like people are not careful about their build files. If they're trying to get something to work, they'll just add a bunch of stuff or copy and paste from another build file until their code compiles. And then they move on, check that in, without ever checking whether this was actually required. So we thought, well, should we cut some? But I'm sure you've all seen this scene in a movie. You're like agonizing over, like, do I cut the blue wire or the red wire? What do I do? And we thought there must be a better way. We don't know which dependencies we can actually cut. And we could try them all. That sounds expensive and annoying. So we wondered if there was an automated solution. We looked around, and we found this. It's a tool from Google. Looks pretty official. Looks pretty easy to use. So we tried it. And we saw a lot of errors. And you can see here, Basil actually helpfully suggested that we re-add the dependencies back. And we saw a lot of other errors and generated code, Dagger, all kinds of stuff was missing and broken. We were wondering, oh, has someone else had this issue? And we found this post from someone at Google, maybe someone in this room. It says, unused deps has actually not been maintained. It is a non-functioning tool. So we decided to build our own. We creatively called it unused deps with a dash. And we used we're on the Java team at Stripe, and we used Java to build this, and our expertise with Basil, and we needed a place to store dependency information, so we used SQLite. And I'm going to give you a quick demo. So here's how it works. Let's say you own a service, the cards service. It's not a real service. We allow like hundreds of payment methods. But you run unused deps. It tells you, well, here are the dependencies you have. And here are the dependencies you appear to actually be using. And this is how many we think you don't need. And it will produce a shell script that you can then run. When you run that shell script, it uses Bulldozer to delete your dependencies. And if you made a pull request, it would look something like this. So did it help? Does it work? Will it blend? Well, it actually did. It had a pretty big impact on the total container size and total transitive closure of dependencies of a lot of our services. We didn't run it across the whole code base. I'll get to that later. But yeah, we found some services had even like a 35% reduction in their overall dependencies at runtime. And as I said, we didn't really want to run it across the whole code base. We weren't sure if people had like special dependencies they only needed at runtime. We don't have the domain expertise. Stripe has thousands of engineers. So we made this tool available and marketed it a little bit. And people loved it. And you can see here, just over the course of a few weeks, a lot of people have been running the tool and checking in their changes. So I'd love to help you understand how this actually works. And to do this, we have Ian, who's now awake. He built this tool as an intern last year, and he'll be returning to Stripe this coming spring.
Yeah, so I guess I'm just going to talk a little bit about the implementation of this tool, give an overview of the different parts of it, and then talk a little bit about each of those different parts in some more detail. So the first thing that we need to do to find unused dependencies is get the Bazel dependency graph. And I think John and Carl from Spotify talked a little bit about this, but we use Bazel query, and we use Bazel query to get the Bazel dependency graph, and then we put that in our database. And then we need to get the Java dependency graph, so we use a Java compiler plugin to get the Java source dependency graph, and we put that in our database. And then we relate the two graphs. So we find any edge that's in the Bazel dependency graph, but not in the Java dependency graph. And then we can mark those as unused and remove them. So it's a pretty simple process, but has some interesting details in it. So first, to get the Bazel dependency graph, we use Bazel query. You can pass to Bazel query the output proto flag, and this is going to let you read in the Bazel dependency graph into memory and do whatever you want with it. For us, we wanted to persist it to the database, so we persisted the nodes and edges of the graphs, where the nodes were the Java libraries, and the edges were the dependency relations between the Java libraries. The interesting part was making the Java source dependency graph. So we start off with a bunch of Java files. Here's a bunch of just example Java files. And those Java files are going to have classes defined in them. They're going to have methods, fields, and those methods are going to reference other code. And so we want to figure out, what does each file depend on? What are the other files that that file depends on? And to do that, we need to plug into the Java compiler. So the Java compiler lets you pass a plugin option. A lot of you have probably used a compiler plugin before. Error-prone is a very famous example of that. Basically, compiler plugins allow you to perform some extra static analysis on your Java code in addition to the static analysis that the compiler performs. And the static analysis that we wanted to perform was collecting all the imported and exported symbols for every file. So an imported symbol is any symbol that you use in a file that you don't define in that same file, meaning it was defined somewhere else. So any method invocation, field reference, a class instantiation, anything that you use in a file that was not defined in that same file is an imported symbol. And then exported symbols are just any non-private symbol that you define in that file that could conceivably be imported in another file. And imported symbols are not just like the things that you list in your import statements at the top of the file, or even the list of things that you reference directly by name. It could also be the types of fields that you reference, the types of parameters to methods that you invoke. There's a lot of information that the compiler needs that might not be immediately obvious. So anyway, our Java compiler plugin collected all that information. We store that in our database, and we can use those imported and exported symbols as incoming and outgoing edges in our Java source dependency graph. So now, in addition to the Bazel dependency graph that we got from Bazel query, we now have the true ground truth Java dependency graph between Java files. So then all that remains is relating those two graphs. And we have the mapping between Bazel Java libraries and Java source files. So we're able to relate those two separate graphs and examine them and look for the edges that are in the Bazel dependency graph between Java libraries or Java binaries that are not present in the Java source dependency graph. And so in this example, if we're cleaning up the dependencies of that top node, we can see that there is an edge in the Bazel dependency graph that's not in the Java dependency graph. And we can mark that as unused and then remove it. And so that's kind of like a quick worked through example of how the tool actually works. And as Keith said, we were able to run that on different parts of our code base and find that a lot of the dependency edges that were in our Bazel dependency graph were actually unused. So yeah, thank you so much. And if you have any questions, you can come talk to us afterwards.